Welcome everybody to section 8.3, the number e. So in this section we're going to be learning about something called the number e, and we're going to use it in several ways. So we're going to be doing exponent properties with e, we're going to be graphing it, and we're going to use e in a compound interest formula that I'll show you later. To start off with, let's do a quick warm-up. I'd like you to pause the video and try these warm-up questions and see what you can do with this. Okay, if you have unpaused, let's check your answers. Add the exponents when I'm multiplying. Here I'm taking a cubed root and I end up with 3x cubed y to the fourth. Here I end up with 27x to the negative 6, and remember, 27 has its own exponent, so that does not move to the bottom, only the x to the 6 does. And last but not least, for this problem, when we simplify, we end up with 1 over 3x. Alright, I want to show you the number e. So I'm going to show you something right now. This is optional to write down. You can just watch if you want to. So I want to show you something here. So let's say I was trying to do an exponential problem, and I'm starting off with 1 plus 1/10 to the 10th power, and I'm going to figure out what that is, and I end up with that number 2.594. Okay, I'm going to do it again. This time I'm going to have the bottom number be 100. And quick note, this is from that formula we learned the other day, the interest formula where you're compounding and then the n is on bottom and the n is the exponent as well. Alright, so when I solve this, I end up with 2.705. Let's go again. I'm going to now make n 3000, and this is leading somewhere in case you're wondering. Alright, and basically what I'm trying to show you is, and I'm going to stop there, but basically, as n gets bigger and bigger and bigger, as n gets bigger, this answer approaches the number e. And as this gets bigger and bigger and bigger, it approaches the number e, which is 2.71828 ... E is a number just like pi. You know how pi on your calculator is 3.14 something 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 something? E is a number like that. So mathematicians, well, you personally might not use it in your life, but if you go into finance, it's used all the time in different formulas. So instead of people having to type out that number every time, they've just made a symbol on our calculator. Here, if you look at your graphing calculator right now, I can show you where it is. It's actually on your calculator in two places. So first of all, E is the shift key of the divide by symbol. Look at your calculator. E is the shift key of the divide by symbol, and if you just type that in and hit enter, your calculator will show you 2.71828 something something something. The second place E is on your calculator. On the left side of your calculator, kind of near the on button, there's a ln key, and it says e to the x. There they have made for you a e with a pre-typed in exponent, so that if you're trying to do e to some exponent, it just makes it slightly faster, milliseconds faster, but so that we'll use later. Alright, now to start off with, we're going to just be using e with some different exponent properties that we actually learned in Chapter 7. So this part is actually just a review from Chapter 7, but what you need to know is e acts just like an x. And we're not actually going to type this into our calculator and find a number, we're just going to try to simplify right now. So if I look at this first problem, I'm going to use the same exponent properties we already learned. So e cubed times e to the fourth. Remember, you add the exponents. The final answer is e to the seventh. Remember, when in doubt, write it out. I got 3 e's times 4 e's, that's why it's e to the seventh. Alright, and now they're going to make things a little bit more complicated for you. So I want to show you, to start off with here, I look at my 3, and 3 has nobody to combine with, so I know that's just going to be there. But now look at your e's. So remember, we can take the top exponent, subtract the bottom exponent, and we can still do that even if there's x's there. So e to the 2x minus 1x, and so e to the x is the answer, and that's positive, so that stays on top. Next example. For my numbers, 10 divided by 5 is 2, and for my e's, e cubed divided by e squared, I'm in my mind thinking 3 subtract 2, which is a positive 1. That's positive, so it just stays there, and I don't have to write the 1. I could just put that down. All right, next. This, again, looks kind of weird, but remember, if I have two things multiplied together like that, you add the exponent. So I've got 2x plus 3x minus 1. 2x plus 3x is 5x, and that's all I can do with that problem. We could split it up. All right, let me tell you something quick. This, if you have that as your final answer, I will accept it, but technically I guess we could split it up like this, and then that would become e to the 5x divided by e. So if this was a more advanced class, I'd be forcing you to do that, but for this class, if you leave it like that, that is sufficient. All right. Fifth, I've got 2 times e to the negative 4th to the negative 1 exponent. First of all, I'm thinking distribute. Because it's multiply, it's allowable to distribute the exponent. Negative 4 times negative 1 is 4. And here, e to the 4th stays on top while the 2 to the negative 1st moves to the bottom because of the negative exponent. Last but not least, I'm going to again distribute my exponent, so I have 3 squared, and then remember, I didn't mention this before, I'm assuming you remember, but when I say distribute, it's a power to a power, so I multiply them. So negative 4x times 2 would be negative 8x. And now I have a negative exponent, so 3 squared, which is 9, stays on top, but the e to the 8x goes to the bottom. Now this part, we're definitely going to have to practice more in class. So that part we will practice more in class. The rest of this section is all about graphing and using some formulas. So the rest of the section is going to be very similar to what we did in section 8.1 and 8.2. Okay, so a natural base exponential function, and by the way, I didn't even say this earlier, let me scroll back up. The number e, that is called the natural base. That is called the natural base. So if something in your book talks about the natural base, they're talking about the number e. We're going to make a general formula like we did when we were doing 8.1 and 8.2. So here I've got a times e to the x power. That's kind of my general formula. And it's similar to what we did before in that that is still the y-intercept. And also, I'm going to right away tell you, we're going to be doing up, down, right, left with this like we did before, and same rules apply as we did in 8.1 and 8.2. So if I do have a translation in the exponent, a plus moves it left and a minus moves it right, and outside of the exponent, a plus moves it up and a minus moves it down. And now we're going to actually, to graph it, use the same step-by-step we did the other day. So step 1, find the y-intercept and plot it. Step 2, find another point. And I'll show you in a second, it might seem weird, but we actually can just plug in 1 still and find a number. So I still recommend using 1 just because it's fastest, but you could use anything you want to. But I recommend you use 1 for x and then go ahead and find y with your calculator. All right, and we're only graphing those 2 points. So again, we're going to graph 2 points and draw on the shape. So let me just show you a graph before I have any numbers or anything. So I'm going to show you y equals e to the x and y equals e to the negative x. All right, so first thing I want to point out is because e is going to always be e. So in section 8.1 and 8.2, do you remember how the b value determined if it was growth or decay? That's not going to happen here because e is always going to be e, 2.718. So it's always going to be greater than 1. It's going to be the same thing every time. The thing that determines if it's growth or decay is the variable. So if the variable is positive, it is growth. And if the variable is negative, it's going to be decay. And I'm going to do, that's why I chose these two, because I want to do one of each type. All right, so, and these are kind of like a quote parent function if you want to think about that, but all of our graphs are going to look very similar to these. So I'm going to follow my step-by-step. Step 1, find my y-intercept. There is no a value, so I'm thinking it's 1 times that. So my y-intercept is 0, 1. Step 2, I'm going to find my other point. And my other point, I'm going to again use an x value of 1 just because it's fast. And I'm going to, just like we did in 8.1 and 8.2, I'm going to plug in that variable. And then this is where I'm going to type this in my calculator. So your choice which E button you use. A reminder again, if you want to use the E that already has the exponent preloaded, on the bottom left side of your calculator, it's the shift key for the LN button. It's the shift key for the LN button, and it looks like this. So in my calculator, what I would type in, it'll look like this. And that's just e to the first power, which is just e. So that's going to end up being 2.718. And because of the e being a decimal, all these are going to be approximate for the other point today. All right, so 1, 2.7, there it is. I'm going to now draw in my general shape. And this one looks like exponential growth. And then I'm going to find the domain and range and the asymptote. Okay, so this one has the same asymptote as a normal exponential growth function. So the asymptote is at y equals 0. And the domain and range, the domain is all reals. So, you know, you need to know that an E graph, it is an exponential graph, just like we did in 8.1 and 8.2. It just happens to always have a base of 2.7182. But it is an exponential graph, so kind of same rules apply. So the domain is still all reals, and the range, I'm looking at where my graph is. I know it's going to be values greater than 0 if I see my whole graph is above that asymptote there. So I'm going to say y is greater than 0 for the range. All right, for decay, this has as well a 1 for the a value. So my y-intercept is 1. And then to find my other point, I'm going to plug in a 1 again for x. And so in my calculator this time, it's e to the negative 1 power. E to the negative 1 power. And that ends up being 0.4 if you round it. So 1, 0.4. And so my graph looks something like this. See how it looks like decay? And the asymptote hasn't moved. That's at y equals 0. And the domain and range are actually the same. So the domain is still all reals. And for the range, it is still, even though it's going the other way, all the y values are still above 0. That's what we're looking for. So y is greater than 0 still for my range. All right, so let's quickly talk about growth or decay. And I know on here I said to find the y-intercept and find one other point, but we're actually going to do that 4 more times on the other side, so we're not going to do that step. I just want to say growth or decay. So based off of what I just said, go through quickly and pencil it in, pause, pencil it in. What do you think for each of them? All right, let's check your work. Decay, growth, decay, and see how it doesn't matter what's in front of it. All that matters is the exponent, and this is growth. So even though there's a negative 3 in front of there, that doesn't make it a decay function. It will make the graph a little different. If you have that negative in front, it does flip over the x-axis, but it's still considered a growth function, because remember from the other day, my growth could look like that, or if I just took that same exact graph and mirrored it down this way, both of those are considered growth. So this one with the negative in front would look like that, but it's still considered growth. I know it's kind of weird. All right, go ahead and stop the video, and I'll meet you with part 2 on the back side. Thanks. Hey everybody, welcome to 8.3 part 2. By the way, I was reviewing my 8.3 part 1 video, and did anybody count how many times I said the word so in that video? I thought that was pretty funny, so you can make fun of me for that tomorrow. I'll try to cut that down for this video. Our first example here is just actually a continuation of what we did on the front side. So the first 2 graphs are just like what we did on the front side. So if you feel up to the challenge, pause the video and go ahead and try these 2. Alright, if you have unpaused right now, for the first graph, remember step 1, plot your y-intercept. In this situation, that is 2. For our second point, I'm going to find another point. I'm going to use x is 1. when I plug that in, I end up with a point of 4.23. 2, 3, 4. Draw in my graph. And I didn't tell you to do this, so you may not have done this already, but let's find the asymptote and the domain and range. So the asymptote is still at y equals 0. It has not shifted up or down at all. And this is an exponential graph, like I said earlier, just like all exponential graphs we've done in 8.1 and 8.2. So the domain is all reals. The range, this is above the y equals 0 line, so it's going to be y is greater than 0. Alright, let's check your work for part B. First of all, it doesn't really have a y-intercept, though it has that negative right there, so that means that the y-intercept is at -1. When I find my other point, I type this into my calculator, and you should end up with -0.02. And so my graph looks something like that. Quick troubleshooting tip: if you keep getting the wrong number here for your second point, double check this, because according to order of operations, we have to multiply this together. We want that whole thing as part of the exponent. So in your calculator, that should be together. Of course, I hope you do not have to type in -4 times 1, but if you do, it should look like that. Let's do the domain, range, and asymptote for this one. So my asymptote has not shifted. It's still at y equals 0 this time. My domain is still all reals, like all exponential graphs. And my range, this time it is below that line. That means that y is less than 0. Let's move on to some where we have to do up, down, right, left shifts. I'm going to teach this like what I did in 8.1 and 8.2, which means I'm going to graph it first without the shift, and then I'm going to shift it. And only your final answer is required, so if you do not want to graph the original one, you do not have to. When I say that I want to shift or graph the original without the shift, in this situation I mean just this part of it. So what I would do is first graph y equals 3 times e to the 2x, and let's go through that quick. So y-intercept is 3. Oh, and one quick comment. This graph, when I do point 2, I actually end up getting 22.2. So we're going to have to make the scale on my graph different than normal. So I'm going to make the scale on my graph up by 5, 10, 15. So actually each tick mark is 2.5, which might make things a struggle in a second, but whatever, we'll figure it out. So my y-intercept is at 3, and the second point is at 1, 22.2, so something like that. Alright, this is my graph without the shifts. So that just represents y equals 3 times e to the 2x. Now I'm going to do the shift. So step 1, graph it without the shift. Step 2, shift it. According to these rules that I gave you on the other side and from 8.1 and 8.2, I see a minus sign, so that means right 1, and I see a plus sign, so that means up 2. So each point I'm going to go right 1, up 2. And I have not yet labeled the x-axis, so I wrote stuff down without even saying anything. I'm assuming right now that the x-axis is labeled normally. Alright, we're going to go right 1, up 2 for each one of the points then. Right 1, up 2. Just do the best you can. And then because I've moved up, my asymptote also has shifted up. So make sure you draw on your new asymptote. And that's the line that I can use as a guide when I'm making my final answer now. So I know that the tail goes right along that asymptote. I'm going to now find my domain and range. It's still an exponential graph. Domain is still all reals. I'll give you a second. What do you think the range is? What do you think the range is based off of what we have done? I hope that you're kind of becoming an expert at this right now. Oh, you know what? I just made a mistake. I made 2 mistakes, really.
Do you see it? Okay. The asymptote actually went up 2, so my asymptote should be at 2. And then the other mistake I made was I graphed it as if the scale was 1, 2, 3, 4, 5, but it's not. The scale goes up by 5. So y equals 2 is a line kind of like right here, actually. That probably does not really change your picture because that graph is so tight right there anyways, but I'm glad that I've caught that mistake. Did you come up with the range? The reason I thought of that mistake was I was thinking, oh, it goes up 2, so the range should be up 2, but my asymptote I had incorrect. That's how I realized that. All right, pause the video and try the next one on your own. If you are ready to listen to the next one, here's what I'm going to do. First, I'm going to graph it without the shifts. And when I graphed it, I found a y-intercept of 0, 1/4. And I found my other point. It's very, very small, so this is a difficult one to plot. I actually ended up with 0.01. So I just plugged in the 1 in for the x here, and I used my calculator. But that is going to be kind of even hard to draw, but there it is. Do the best you can. So this was my graph without the shifts, so that is not my final answer. Next, I do not have a left or right shift because there is no k or h value, but there is a down 1 there for that k value. So this is going to be shifted down 1. I'll draw on my asymptote first, and then each one of these dots I'll shift down 1, down 1. And again, do the best you can to draw in the graph. There is my final answer. Asymptote is at y equals -1. Domain, all reals. Range, y is greater than -1. Please write down any questions you have on that and pause the video. Make sure you have that all written down. When you're ready, move on to the next section. Next, we're going to show you how E applies to interest and finance. So the thing is, remember yesterday, or in section 8.2, we had this formula. All right. Okay, I'm struggling here. So I had the principal 1 plus r over n to the nt power. Now this part right here is what's going to get replaced by E, because basically what I tried to show you on the front page was that as n gets bigger and bigger and bigger, this number in here gets closer and closer and closer to E. So we're going to be talking about something called the continuously compounding interest formula, and imagine yourself trying to compound interest continuously. So if I asked you how many times per year has my interest been compounded, even if it was once every second for the whole year, that would be a huge number for n. So E replaces that part of it. My formula looks like this then. A equals P times E to the RT. So again, this whole part just got replaced by E. Some students like to call this the PERT formula to remember it because it looks like the word PERT. Okay, P is still the principal. And R, or starting amount, I think on 8.2 I called it the starting amount. R is still the rate as a decimal. And for this formula specifically, T is always in years. You might remember the other day when we had the general formula. I'm forgetting what variable we used, but something like that. Remember I said T doesn't have to be years? For this formula, T does have to be years. So specifically, the formula was created that way. So if you get something like 6 months, use 0.5 in the formula. So here's a few examples of this. You deposit $1,000 in an account that pays 8% annual interest compounded continuously. What is the balance after 1 year? So this is actually quite an easy problem, but the thing is, when you test on this, you're going to have to be able to identify this and know that if it says compounded continuously, you're going to specifically use this formula. So I'm going to go ahead, plug in my starting amount, plug in my interest as a decimal, and I'm going to plug in my time. And note, these have to be multiplied together when you're typing it into your calculator. So let's say that I want to type this in my calculator all at the same time. Now, you don't need to type in times 1, but if it was a different number and you needed to use it, you want to put that together in the parentheses. You should end up with $1,083.29. Why don't you type that in and make sure you can get it correct. The next one, go ahead and try on your own quick. If you have unpaused and you're with me now, here's your setup. And for a final answer, you should have ended up with $1,530.30. Here's another application. Sometimes they give you a formula already. So for this last example on our notes sheet today, it says, since 1972, the U.S. Fish and Wildlife Service has kept a list of endangered species in the United States. For years 1972 through 1998, the number S of species on the list can be modeled by this equation, where T is the number of years since 1972. That's important. All right. They gave us a formula this time, and now we're going to use that in some situations. First of all, what was the number of endangered species in 1972? In disguise, 1972 is our starting year, right? So in disguise are asking us, what was the starting number? And we know the starting number in our formula comes before the E. So we can't have 0.6 of a species, but that must be some average or something. So approximately 119.6 species in 1972. Next question, what was the number in 1980? So first I got to ask myself, how many years past 1972 is this? It is 8 years past 1972. That means T is 8. I am going to use the formula and plug in an 8 for T. And again, this is what I was saying earlier, where you got to make sure that this 0.0, both of these parts in the exponent are multiplied together in the parentheses there. But now if you type that into your calculator, you should end up with 249.07. So let's say approximately 249 species. So it's kind of sad that in 8 years during that time period it increased to 249 species that were endangered in the US alone. All right, part C, estimate when the number of endangered species reached 1,000. Okay, so this is like what we did. We've hopefully done a few of these by now. This time they gave me the ending amount. So I'm going to take my ending amount, the S in my formula, and this time T is the missing variable. And in order to do this, at this point we don't know how to solve this yet, so we're going to do some guessing and checking. And when I think about this, we know that 8 years was 249. So let's be smart about this here. 8 years was 249. So I'm not going to guess 9 right away because I don't think it's going to be 9. Maybe 15. And I don't know, I actually didn't do this one ahead of time. Usually I'm very prepared, not this time. So I'm going to just guess and check and see what we get here. And actually I'm almost out of time, so I'm just going to tell you we should get approximately 23 to 24 years. So that was 1995 to 1996. Okay, thanks for listening. Talk to you next time.